Have you heard about the Putnam Competition? The Putnam Competition is a mathematical competition that's designed for American undergraduate students, and it's said to be one of the hardest mathematics exams in the world. And today we're going to take a look at the exam and we're going to answer some of the questions in it. Let's dive straight into it. Hi everyone and welcome back to my channel. For those of you that are new here, my name is Ellie and I'm a Cambridge mathematics graduate, and I use this platform to nerd out about cool maths, physics, space, STEM stuff. So if that sounds like something you're interested in, then subscribe down below. So the exam itself is taken by American undergraduate students who are already specialising in mathematics. The exam itself is 6 hours long, which is ridiculous. It comprises of 12 different questions, and those 12 questions are split up into 2 sections. So there's 6 questions in section A and 6 questions in section B. All questions carry equal weighting and they all are marked out of 10. So the maximum score you can get on this exam is 120. Despite the plethora of exam marks available, the median score on this exam is between 1 and 2 each year. So yeah, you might be thinking, this is going to be a hard exam. And you won't be wrong. The questions are designed to be particularly hard. The questions go from 1 to 6 in each section, and they're designed to get harder, although that is up to the interpretation of the person who's sitting the exam. Now, the exam itself offers cash prizes and the opportunity to become a Putnam Fellow, and the top 5 people in this exam go on to be Putnam Fellows. I'm sure many of you have heard of Richard Feynman, and he is actually a Putnam Fellow, along with 1 other Nobel Prize winner and 3 mathematics Fields medals. So yeah, if you get high marks in this exam, you probably have a pretty bright future ahead of you in mathematics. So here is the exam from last year, which was 2023, and this is it, 1 page, and it has 12 different questions, and as you can see there's 6 for section A, so we have A6 here, and 6 for section B. Now you can pause the video, you can take a look at it, try to tackle some of the questions for yourself, but today I'm going to be focusing on question A1 and A6. I decided to try one of the easiest and one of the hardest questions in the exam just to give you a bit of a taste of what you have to answer. By all means, this is not representative of every single exam. You might find the questions that I go through today particularly easy, and if you do, then I encourage you to look at some other questions in the Putnam Competition and see how you do on those. As I've just explained, the Putnam Competition is a mathematics contest. Brilliant.org have courses on contest mathematics that give you the opportunity to tackle advanced mathematics problems, those that you'd expect to see in such competitions. Brilliant also have courses across a range of STEM subjects, including mathematics, science, computer science, and you can even learn how to code. I personally love the interactivity of the courses that they have on offer. Did you know that interactive learning is 7 times more efficient than simply reading course material? If that sounds like something you're interested in, Brilliant are kindly offering you watching this video full free access to their entire platform, which includes all of their courses for free for a full 30 days. All you have to do is click on the link in the description box or in the pinned comment, or head to brilliant.org/Ellie Slightome, and the first 200 of you that sign up will get 20% off Brilliant's annual premium subscription. So thank you, Brilliant, for sponsoring this video. Now let's get back to the maths. Okay, so this is question 1 on the Putnam Competition, and I've just got a screenshot of it here, and it says, for a positive integer n, let fn of x equal cosine x, cosine 2x, cosine 3x, multiplied by all the rest of them up until cosine nx. Find the smallest n such that the modulus, so the absolute value of the double differential of fn at 0 is greater than 2023. Quite nice they've put the number 2023 in here, because that is the year that we're doing it. And I think that might be a theme across some of the Putnam competitions, is they always seem to include the number of the year that it is. What I'll do is I'll just write out what f of n is, so we have it there, but I'm going to take this video a little bit slowly, just so people that don't have a massive background in mathematics can follow this along, and hopefully you can understand some of the maths that goes into one of the hardest mathematics exams across the world. So we have all the cosines multiplied by each other, and every time you multiply a new cosine, the value inside the cosine, it kind of increments. So you have 1, 2, 3, up until cosine n. And what we need to do is we want to find the double differential of this function. So we want to find double differential. So we want to differentiate this equation, this function, twice, and then what we'll do is we'll add x, or we'll input x equals 0 into here, and that will help us get this here. And then we just need to find out at the point at which this is greater than 2023. So that is the setup of this problem. Okay, I want to take this piece by piece. Now we can jump in straight away and get the solution almost immediately, but what I want to do is I want to show you an example for f2 of x, so when we only have two cosines in here, and just show you what's going to happen when you differentiate them. So we're going to start by showing the example for n equals 2 in this function. So first we're going to consider f of x cosine, and I'm going to just put here m1 of x cosine m2 of x. Now you can say that this is f2 of x, or this equals f2 of x when m1 equals 1 and m2 equals 2. But for the sake of the fact that we have a 1 in here, and sometimes when you multiply by things by 1s, you don't really necessarily note that you've multiplied it by 1 because it's exactly the same. So I'm just going to generalise this to have m1 and m2 in here. What we can do is we can apply the product rule to differentiate it. So apply product rule. Now I'm going to say that this here is u and this here is v. So when we apply the product rule, what we get is the differential of f of x is u multiplied by the differential of v with respect to x plus v multiplied the differential of u with respect to x. Okay, cool. Now we can do the exact same thing again, and we can say we want to apply the product rule. So we'll say apply product rule again, and that gives us f double differential of x. Okay, now we can apply the product rule to each of these individually. So we can say that if we keep u constant and differentiate this, we get u is kept constant, and we have the double differential of v. And then we can do the same thing, and we can say, well, let's hold this constant and differentiate this. So we end up with du dx dv dx. Now for the second term we can do the exact same thing. We can hold this constant and differentiate this. So we have v and the differential of u twice, so the double differential. And then we can do the exact same thing as we did before and keep this constant and differentiate with respect to that. And you'll note that that is exactly the same as this term here, so we can just put a 2 out front. So for this simplified example here, we have found the double differential of f of x. The final part of the question asks for this evaluated at x equals 0. So if we say at x equals 0, what do we find? Well, we find that the differential of cosine x, we know that this is minus sine of x. Now I should say that's evaluated at x equals 0, and that's evaluated at x equals 0. So that gives us minus sine of 0. And if you remember anything from trigonometry, sine of 0 is always 0. Cool. So all first derivatives must vanish. So I'll just say, therefore, all first derivatives must vanish. So that would mean that this in here, this would essentially go to 0, because this would go to 0 and this would also go to 0. So you'd end up with this term and this term for this. Okay, now that is a trick that you need to note because it's going to help massively when we come to answer the full generalised version of fn of x. Okay, cool. This would imply that the double differential of f of x is, let's have a look. We have u, which is this term here, and then we have the double differential of v. So let's calculate that. So first of all we have u, so that's just cosine m1 of x, and then we want to differentiate v, which is this here, twice. So when you differentiate cosine twice, you get minus cosine, and then we obviously need to multiply out the coefficient that's inside the cosine. We want to do that twice. So we end up with minus m2 squared cosine m2 of x. Okay, and similarly we can do the same, pretty much exactly the same, but the other way around for this term here. So we have v, which is here, and then we have the double differential of u, which is there. Okay, so v is cosine m2 of x, and we want to multiply that by the double differential of u, which is minus m1 squared cosine m1 of x. Okay, cool. Now we can note, again, if you remember your trigonometry, that the cosine of 0 is 1. So that implies that the double differential at x equals 0 will give us, this will just be 1, this will just be 1, as will this, and as will this. So all we get are essentially these factors out front. So we have minus m2 squared minus m1 squared, and of course we can write that, if we rewrite it the other way around, so m minus m1 squared minus m2 squared, what this is doing is essentially taking the sum of minus, and we'll keep the minus out front because we can do that with summations, mn squared, and how many n's do we have? We have 2, so from n equals 1 to 2. So that is the answer here for this generalised version of f of x. Okay, cool. Now I want to show you an example of 3 cosines multiplied by each other, just so you can understand the concept of adding more cosines onto the function itself. For the sake of the video, I want to explain this in a way that everybody can understand. So we're going to consider now g of x, which would be cosine m1 of x, cosine m2 of x, cosine m3 of x. Now, as before, I'm just going to call this A, call this B, call this C. So that's the same as A multiplied by B multiplied by C. Now we can do a very similar thing to what we did before and apply the product rule. So product rule gives that the first derivative of g is, okay, well let's first of all keep this constant and differentiate this. So we have A multiplied by the differential of B and C, and then we can do the same again, and we can differentiate this but hold this constant. So we have plus dA by dx multiplied by BC. Okay, now again we can apply the product rule once more, and we get that the double differential of g of x is a similar approach again. Keep this constant, differentiate this, so that's A double differential BC plus, now what we can do is we can differentiate this but keep this constant, so we end up with dA by dx and dx of BC. Now we can do the exact same thing for this term here, so keep the first constant, so dA by dx, and differentiate the next term, so that's dx of BC, and then vice versa, we get the double differential of A multiplied by BC. Now I should really have put the BC out front here, but for the sake of the video, you know what I'm doing. Okay, cool. Now we can make the exact same statements that we had before, and that is that at x equals 0, the differential of A with respect to x is the same as the differential of B with respect to x, same as C, and that's because they all equal 0. And that is just by this statement that I made here that said that all first derivatives must vanish. So in this example, we have that, where's a first derivative? Here. So this entire term goes to 0, and again, derivative here, that goes to 0. And all that we're left with is this here and this here. So we can say that the double differential of g of x is the same as a d squared, or the double differential of BC plus the double differential of x, and I'm just going to put the BC out front here. Okay, cool, so that is the double differential, and again, when we apply at x equals 0, and I should have just said this is evaluated at x equals 0, just to be consistent with the notation here, because the double differential of g of x, if it's not evaluated at x equals 0, we'll still have these extra terms in, but this is at x equals 0. This equals minus m2 squared minus m3 squared minus m1 squared. And that is because we've already established what the differential of two cosines multiplied by each other are, and that's this term here. And then for this one here, this is just the double differential of cosine of m1 of x, which gives you this term here. And again, we can say, well, this equals minus the summation from x equals 1 to 3 this time of mn squared. This can be generalised to mn equals n, which is what we have in the question, for f of n double primed of x, to get that the answer is this. Okay, so all we've done there is we've just basically said that when we generalise this to higher orders, so to the f of n of x that we have in the question, the first derivatives always cancel, because when you evaluate sine at 0, you get 0, so they always cancel. And then when you have the remaining terms in the function itself, they reduce to this summation here. And we've shown that for the n equals 2 case and the n equals 3 case. And obviously then as you increase the number of n, the same holds. So we can say that this is what happens. Now, something I want to mention, because I worked with mn here instead of n, I just said here it can be generalised for mn equals n, because obviously I had m1 for when we had n equals 1, and then I had m2 when I had n equals 2, and so on. So I just substituted this in here just to be consistent. So yeah, this is the full formula for what is asked in the question. And now what it wants us to do is determine when this is greater than 2023. So the first thing to note is, and you might remember this just from the series of the summation of squared values, and that is that the summation that we have on the right hand side here is n plus 1, n plus 6, all divided by 6. And again, this is essentially the same as this, because we have the minus out front gets cancelled by the absolute values here. Okay, so we want to know when this is greater than 2023. Now you can calculate this by substituting in values, which is probably, I guess, the faster way. You could do it by doing a cubic root substitution in this, but that might take a bit too long. See if you can try it at home and see if it was faster than substituting in values. But what you essentially get is that at n equals 17, this is 1785, and at f, when n equals 18, we get 2109. So from this, we can say that this holds true when n equals 18. So there we go. That is the full answer to the first question. Like I said, I went through this in quite a slow way. I showed examples of what happens when you multiply for n equals 2 and for n equals 3, but you could have jumped straight into this and just spotted that the first derivatives must always cancel, and that you end up with this formula here for the function, the double differential of the function at x equals 0. But yeah, I thought I'd dive into a little bit more of the intricacy of it and show you some examples. And it's a really, really nice question. It definitely takes some thinking about, but I really liked it. As first questions go, I thought it was really nice. So now we have done question A1, we're going to be looking at question A6, which requires a bit of thinking about, really. There's a lot that you need to wrap your head around in this question, but the concept itself, I thought, is quite a simple concept, but there's a lot of thinking behind it. And yeah, let's have a look at the question now. So the question says that Alice and Bob, classic names that they use in mathematics, play a game in which they take turns choosing integers from 1 to n, so from 1 to n. Now, before any integers are chosen, Bob selects a goal of odd or even. On the first turn, Alice chooses one of the n integers, and then on the second turn, Bob chooses one of the remaining integers. And then they continue alternately choosing one of the integers that has not yet been chosen until the nth turn, which is forced and ends the game. It says that Bob wins if the parity of this, so k, where the number k was chosen on the kth turn, matches his goal. And it says, for which values of n does Bob have a winning strategy? So yeah, that might have seemed like a lot of words, but I'll show you what happens exactly. So first of all, let's do a little example of this situation and what is going on. So the example is that let's take n equals 8. So the idea is that Bob and Alice are playing this game and they have n numbers, so n integers from 1 to n. So for the n equals 8 case, we'd have 1, 2, 3, 4, 5, 6, 7, 8. And then what happens is Bob, before he starts this game, he says, okay, I choose even or odd. It's a goal that he's going to choose. And it remains a bit irrelevant for now, but let's just say Bob chooses even. Let's just say he chooses even for this example. So then Alice takes her turn. So let's just say this is Alice, this is Bob, and we're going to say like this is the first and second turn, this is the third and fourth turn, this is the fifth and sixth turn, and this is the seventh and eighth turn. So Alice first, let's say she picks the number 8, then Bob chooses the number 2, Alice then says, okay, what's left? Let's choose 3, Bob chooses the number 5, Alice chooses the number 1, Bob chooses the number 6, Alice chooses the number 4, and Bob chooses the number 7. So what's happened here is essentially they've taken it in turns to pick the numbers that are left out of this range here. Now, what happens is, for this parity of k, it's the number of times that either player has selected the number that corresponds to the turn that they took. So firstly, Alice chose the number 8, so that does not correspond to the first turn. In the second turn, Bob chose the number 2, which does correspond because Bob has chosen number 2 on his second turn. So if we just write a little note here and say, we'll denote 0 if the number k wasn't chosen on the kth turn, but we'll denote it 1 if it was. So 3 on the third go, so Alice chose number 3 chosen on the third turn. 5 for Bob on his fourth turn, no. 1 for Alice on her fifth turn, no. 6 for Bob on his sixth turn, yep. 4 for Alice on her seventh turn, no. And 7 for Bob on his eighth turn, so no. So here we found that if we add up the times that the number k was chosen on the kth turn, we have that there were actually 3 times that happened. And the number 3 is odd. Now what did Bob select when he first started the game? He chose even. So in this case, he would have lost. But that illustrates the example that we have here. Essentially, we just have a list of integers, and Bob and Alice take it in turn, selecting some of these integers, and if the number they choose corresponds to the number in their turn, we add a 1 to the whole number of times that's happened, and then at the end we see whether that whole number is even or odd, and if that matches what Bob selected to begin with for his goal, then he wins, but if not, he loses. And the question asks, does Bob have a winning strategy? So can he formulate some sort of method that he will stick to during this game, which always results in him winning? And the answer is yes, and we're going to have a look at it now. Now the first thing we can kind of note, and we can say, is that the number of times k is chosen on the kth turn is exactly the number of fixed points of the permutation of 1, 2, and so on up to n. So as an example, if we took, say, n equals 3, so say we had 1, 2, 3. So the question is, what are the permutations of this? So, Alice could go first and choose 1, then Bob choose 2, then Alice choose 3. Or it could be 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So I've just written the permutations for n equals 3 down there, and each time, like each of these incidents, we can see, okay, well, how many times is k chosen on the kth turn? So here we have, well, that's 3, that's 1, that's 1, that's 0, that's 0, and that's 0. And that is something to note for this problem. Now, let's kind of consider a few different scenarios. So firstly, we have case 1, which is when the number of integers that both Bob and Alice have to choose from is even. So if we say that n is even, so for the sake of the video, I'm just going to write out the number of integers that Bob and Alice have to choose from, and this is for when n is even. Okay, so Alice goes first. So what are the options that, like, what can Alice select? So if we say, what can Alice actually select? So she goes first, she's got this whole number of integers. She can either choose one number that does correspond to her turn, which would be 1, or she can choose another number that doesn't correspond to her turn. So any of the other numbers that are available. So let's write that down. So the first thing that she can do is she can select a number k on the kth turn, or she can select a number j, which does not equal k, on the kth turn. So those are her two options. Now, it's very important in the question that we are told that Alice goes first, because what that means is all of her turns are when k is odd, and for Bob, all of his turns are when k is even. So we can kind of exploit this even-odd step and essentially look at this. And we can look at the number of integers, and we can split them up into pairs. So what we can say is, if we say, okay, the odd numbers are 2k minus 1, the even numbers are 2k, and we can separate them up and say 1, 2, that's a pair, then we've got 3, 4, that's a pair, and so on until the end. And we can separate them into pairs because this is for the case when n is even. So what happens if Alice does choose k on the kth turn? Well, if she chooses 1 on the first turn, that means that the total number of values where k has been selected on the kth turn is 1. Now, Bob could be quite clever and say, well, what I'll do then is I will choose the next term along in that sequence, which is 2, and therefore he's also chosen a number k on the kth turn, and therefore the total number of k being chosen on the kth turn is 2, so it's even. Now, what happens if Alice didn't choose k on the kth turn? So say she chose 2 on the first turn, well, that would keep the number at 0, so it would still be even, and Bob could then choose the number that was before that, so he could choose 1 on his second turn, which therefore keeps the number at 0 and therefore even. So the strategy here is what Bob can kind of do is he can essentially look at what value that Alice chooses and just take the number that's in that pair. Now this is really neat because essentially by working in this pair strategy, you will always keep the number as even, so Bob can select the number even. So the strategy here is Bob selects a goal of even, and if Alice selects a number 2k minus 1, Bob selects the other number in the pair, which is 2k. And if Alice doesn't, Bob chooses the other number in the pair. So that is Bob's strategy for when n is even, and this strategy is really neat because essentially it allows you to take advantage of this pair situation, and whenever Alice chooses a number that is not k on the kth turn, by choosing the other number in that pair, Bob is also doing the same, so we'll keep the number of fixed points at 0. But when Alice does choose the number k on the kth turn, Bob's turn is next, and if Bob chooses the next number in the pair, that will also be k on the kth turn, and therefore increment the number of fixed points by 2, so it's always going to be even in this strategy, and that's why Bob selects a goal of even. So that was the case for when n is even. Now what do you think the solution is for when n is odd? Now I'm going to be making a separate video on the full solution to this question, so if you're interested then subscribe down below to check it out, but let me know in the comments what you think the solution is. But that was the Putnam exam competition today. I hope you enjoyed the video. If you did, then please like, subscribe and comment, and I'll see you all in the next one.